Hi everyone, my name is Kyle Benak, or you might know me as B3Neck on Twitter. I'm a full-time security researcher and I really enjoy testing Android applications in my spare time. I'm really excited to be presenting my Exploiting Android Deep Links and Exported Components talk here at Ekoparty. Now what I'm about to say next really applies well at this conference. Let's get the party started. I always like to start with a brief overview. I'm going to go over the tools I use in my workflow. Then I'm going to explain the Android ecosystem and how it works with the applications that are installed. Lastly, we're going to get to the good part, which is exploiting various parts of an Android application, which involves web views, deep links, and third-party integrations. These are the tools I use in my workflow. I use JADX for static source code analysis and to decompile APKs. I use Android Studio for proof of concept development and the AVD emulators that are included. Next is ADB, or Android Debug Bridge, which is essential to pull APKs off of your device through USB after they're installed from the Play Store. Objection is great for patching APKs without a rooted device. After Objection patches the APK, you reinstall it, and then you can proxy requests from your device. Frida is awesomely epic for dynamic analysis and dynamic runtime analysis. Burp Suite, like I said earlier, after I patch the APK, I can forward the traffic from the device or an emulator to Burp Suite that's on my desktop. DB Browser for SQLite is great for reading databases that you find in public storage, which we will cover more later. Custom bash scripts are essential for automating all the redundant tasks. And this includes like pulling APKs off of a device, renaming it from base.apk to the actual name, and then um, even reinstalling it. Physical devices I use are a Galaxy S10e, a J3 Orbit test phone, which at the time was $50 on Amazon, and AVD emulators. Next, we're going to talk about the Android ecosystem. So, each app is isolated to its own security sandbox or VM. Each app also has its own process and unique user ID. And the Android OS uses principle of least privilege, so applications only have access to the components that are required. So you might be wondering, how can Android apps be exploited? Well, once an application exports components, has third-party integrations, also anywhere data is flowing and data is shared, stored, or input that's provided by the user. Remember, never trust user input. Lastly, user provided intent data being used in onCreate or onResume, etc. Those two lifecycle methods are the easiest to exploit in my opinion. Static analysis file recon. So now that we know a little bit more about the ecosystem and the tools being used, we need to know where to look for misconfigurations or insecure implementations. So this is part of the XMI map that I'm going to include for this talk. And the first place I always look is Android manifest.xml because that's essentially a blueprint for the entire application. And here you'll find exported components, API keys, custom deep link schemas, HTTP deep link scheme, deep link host, schema endpoints, deep link path patterns. So all those values you will combine to create exploits or create proof of concepts. Next is strings.xml, where you can also find API keys and custom schemas for deep links because developers are actually encouraged to store hard-coded strings as references here. Now let's talk about files path.xml. So this is where you can find out if files Especially sensitive files are being stored in external storage, which is public storage. The key words to look for is external path and external files path in files underscore paths.xml. And programmatically, you could also recursively search for environment.get external storage directory. Now, network security config.xml will tell you if clear text traffic is permitted, which can be very bad for obvious reasons, especially if there's sensitive data sent back and forth. And lastly, you want to search all source code recursively, especially the build config files. Exporting components. So declaring components as exported with Android export equals true makes other Android applications able to access them. And this property cues researchers in to know that they should audit the source code for that activity or for that component. Because depending on the implementation, it could be vulnerable. And these are the type of components that could be exported and vulnerable. First is activities, and this is what I'm going to talk about most in this talk. An Android activity acts as an entry point to a specific part of the application. Export activities are very similar to deep links, except an activity actually handles a deep link via intent filters. And then the application logic determines what happens with the data, with the intent data, most of the time. Services supply additional functionality in the background. Broadcast receivers receive broadcasts from events of interest, usually specified broadcasted intents in the broadcast receiver activity. Content providers help applications manage access to stored data and ways to share data with other Android applications. How deep links are set up. So deep links are declared with intent filters and have the following attributes. And one unique feature to all deep links is that they can have custom schemes. So how you usually see HTTP and HTTPS, you can also see on Android that the picture to the left represents this pretty well, is that it has a custom scheme of flag 11. So a deep link can be crafted with flag 11 as the scheme, and then anything provided after that, the activity will actually accept that intent data. And I will demonstrate this later on during this talk. The picture on the right shows how you can implement a host, a path pattern, and a scheme. And these all kind of act like restrictions for the activity. And the activity will only accept a deep link with those properties. Exploiting Android activities. So one way for sure that an activity can possibly be exploited, as we said earlier, is if it's exported. And you can tell by looking in the activity manifest where it says exported equals true, and then Android name will have the actual class that you will want to do source code reconnaissance with. So in this case, it's exported protected intent that you would want to look at to see if the logic is accepting user provided data. Exploiting protected intents from an exported activity. Now this is where the fun starts. An exported activity that accepts a user supplied intent via get parsable extra can access protected components. Now, this is possible because of get parsable extra accepting multiple intents, and this POC that I have will show that. I would like to note that even though that there's a restriction of the package name needing to be injured Android, other components can be accessible as well because the first intent acts as the doorway to the entire application. Now I had to say this at least once, but there's going to be a ton of demos, so it's demo time. Now I'm going to open my handy dandy emulator and the POC app. Now, let's go over this a little bit. The first intent is accessing the exported component, and the second intent will complete the activity for injured Android. Now, I'll show you exactly what I mean. Now, if we open flag 12 POC, it's going to open the first, it's going to use the first intent, and then the second intent is going to complete the activity. And it's going to say, congrats, you found the flag. Now, this can be further built upon to exploit, especially if there's a JavaScript equals true flag, and we'll cover that more later on in this talk. Exported activity XSS via Webview. When an Android activity is exported and JavaScript is enabled, the Webview may be susceptible to XSS attacks. The combination of JavaScript being enabled and user-provided input is what makes this vulnerability possible. Now, I'm going to show you exactly what I mean. And this first picture shows that JavaScript is enabled, and this is Kotlin, by the way. So if I change the payload to the SVG one, and push it to my device, this will automatically run the POC, and we'll get an alert because JavaScript is enabled in this web view. Now, ideally, you wouldn't want to stop at just alerting one. You would want to try to steal session data and stuff like that to have a more impactful POC. Exploiting Android deep links. Android deep links are like solving a really fun puzzle, and once you have all the pieces in place, the possibilities are pretty much endless. So, this XMind map shows some of the vulnerabilities you can find, and it also highlights the different attributes for deep links that you would want to look for. And once you find all these attributes, most of these attributes can be found in Android manifest.xml. I like to search for : / because especially with custom deep links, you might find some hard-coded deep links with parameters. And when you find parameters, there's more fun to be had. Path patterns that are wildcard are very fun too. And I'll show you why later on in this talk. Proxying requests dynamically through burp is also very valuable in disclosing different types of links and deep links that could lead to vulnerabilities. Deep link XSS via Webview. This has the same core concepts as exported activity XSS, except user input is instead accepted via a deep link parameter. And this is highlighted in the first image with get query parameter, which is looking for the parameter totally secure. Now, you'll also notice that this has set JavaScript equals true, which is why this web view is susceptible to XSS. The second image shows the actual HTML POC, which makes it into a remote vulnerability. Now, I will show you exactly what I mean by that on my emulator. I can X out of this real quick and this and open the. Actually, first I'm going to show you how to push the POC to your device. Now, you can use ADB push for this. ADB push the HTML file to SD card download. Now that file is on my emulator, and I just have to navigate back to the files directory, and downloads is already open. And as you can see here, the deep link XSS HTML file is in the folder, and I just have to open it with whatever browser that I want. I always like to zoom in just so it's like easier to click the hyperlink. Now after we click the hyperlink, it's going to go to the deep link schema intent filter. Check that the requirements of XSS and the requirement of whatever is fulfilled, and then get the query parameter totally secure in the application logic. And since the application logic doesn't validate what the payload is, that's why XSS is possible. And I will show you exactly what I mean by requirements. So when you're looking at an activity, and in this case, the activity name is vulnerable Webview, and that's where you'll find the logic source code. The deep link requirements is the scheme of XSS and the host of whatever. And that is displayed in the second image here as well. So as long as the requirements are met, uh, the deep link will navigate to that part of the application. Deep link LFI. This example is inspired by a vulnerability I found in a production application where I could load a sensitive file with a parameter based on the path I gave it. So I could give it a path to a file in a public directory, and the LFI effectively overwrote the file, and that file actually contains sensitive data. And interestingly enough, it overwrote it with only 500 bytes of data and then destroyed the original copy. Now, in this concept, the activity is actually looking for the query parameter of totally secure LFI. It's going to look in the assets directory to see if that file is there. Then it's going to read that file line by line and append it to the web view. And the second image shows what this payload will look like once I push it to the device. And we can go into the manifest again and look for the requirements. So it's the same activity that's looking for the file. So the requirement was just XSS scheme and host of whatever. And I'm trying to show that there's a reoccurring pattern with creating these POCs, and there's a reoccurring way to figure out how to exploit them. So let me open this deep link POC and show you exactly what I mean. So we can ADB push this POC as well. So ADB push deep link LFI to the SD card download directory. Now we just open the files directory and click on deep link LFI POC. Zooming in again and clicking on LFI test will open this application and open whichever file I specify for a totally secure LFI. Deep Link RCE. In situations where custom binaries are in use or commands are being executed via runtime get runtime execute, RCE is possible via deep link. The parameters intent param and binary param are used to execute custom Go binary commands that I created. So I was just curious one day to see if I could create a Go binary and is to see if I could get an Android application to execute them remotely. So I ended up getting it to work. And as you can see here, the deep link is actually looking for the intent param, which is the command that's going to be used by the binary. And the binary param is the name of the binary that I want to execute. And the second image shows the URLs or hyperlinks that are needed to run the commands. And the reoccurring pattern here is that the custom scheme, the custom host needed to match in order for this to work. And also, after reviewing the scheme and the host, looking at the logic shows which parameters can be exploited. So now I'm going to open my emulator again and the Deep Link RCE POC. Zooming in, test one's going to run, each one of these is going to run a different command. So test one will print out treasure, and this is the actual output of the binary. Test two is going to be an underscore. Test three is planet. And to complete this exercise, this is a CTF exercise in Android showing this concept. You would combine all three of these to get the flag. Deep link schema bypass. Under the right conditions, it's possible to bypass scheme validations. In this case, the custom scheme is being converted to HTTPS and the intent is opening a browser, effectively creating an open redirect. This is actually inspired from a recent finding I had where the custom scheme was being converted to a web scheme and I was able to redirect the user anywhere. So as you can see from the first image, the logic is looking for the custom schema or an HTTPS schema. And if it's the custom schema, then it will convert it to a web protocol and the application will then ask the user if they want to open it with a browser. Now the second image shows the proof of concept where the hyperlink matches the requirement of deep link route for the scheme and b3nac.com for the host. Now, like we did before, we will push the file POC, deep link route bypasses that XML or HTML to the emulator. Now we'll open the POC. Let's zoom in and go to the scheme, custom scheme bypass, hyperlink. Click on that. It's going to open the application, ask us if we want to open it with Chrome, and redirect us to the website. Deep link host validation bypass. Same as the scheme validation, the host validation logic in deep link routing activities can also be bypassed. In this case, everything after the scheme is accepted, then loaded into the vulnerable Webview, creating an XSS attack vector. Now, the first image shows that JavaScript is enabled, and it's looking for just it's only validating the host is b3nac.com. Now, because of the lenient validation and that the hyperlink is matching the Android manifest intent filter and the hyperlink is matching the validation in the activity itself, this is passing through with no problem. And the XSS payload is just before the host. Now the POC file is already on the device, so we don't need to push it. We can just go to the host validation bypass, and when we click this, it will ask us if you want to open it with the application, which we do. And you can see it loaded it into the Webview, the XSS payload, because it matched the host validation requirement. Deep link path pattern exploitation. In the instances where there's a path pattern specified in the deep link intent filter of \period *\, it's possible to exploit via XSS. Essentially, this is a wildcard and anything can be used as the path. In this case, I'm showing the Android manifest.xml intent filter because it better explains exactly what's happening. So as you can see, the path pattern activity has an intent filter and the requirements of b3nac.com as the host, path pattern of wildcard after the host, and the scheme of path pattern. Now, this is exactly what you want to check every single time in the Android manifest. And then you can create an HTML POC, like the one in the second image where path pattern scheme is used, b3nac.com host. Then the path pattern of a wildcard can be an XSS payload. And I will demonstrate exactly what happens with this. Now, the POC HTML file is already on the device, so we don't need to push it with ADB. We just have to go to the path pattern hyperlink. Once we click on it, it's going to load in the web view. And when we look at the web view, we can see the path pattern matches, the host matches, and then the SVG is loaded right afterwards. Deep Link CSP bypass. This is inspired from an application that was blocking my deep link requests from my Chrome browser, and I noticed that there was a scheme being accepted of HTTP. So once I changed the deep link to HTTP, it converted it to HTTPS in the application itself and allowed the request to go through. So as you can see from this logic, if I send an HTTP request, it will convert it to HTTPS and then parse the URI and start the intent and ask if we want to open it in the Chrome browser. If it's HTTPS, it won't go through only because it's originating from Chrome, the HTML file itself. So let's test this out. We don't need to push the POC file because it's already on the device. So first let's try the one that should get blocked. So if we click on it, because it's HTTPS, it should not pass the check. So it did not pass the check, which is good. Now if we go back to the one that should bypass it because it's using the HTTP protocol that is specified in Android manifest. It passes the check because it's being converted, and then after it's converted, the request is originating from the application itself. Exploiting third-party integrations. When finding an external API, it's worth reviewing documentation and looking for open source demo apps. Looking at this XMIME map, I've noted a couple different components to look for. Third-party SDKs, it's definitely worth reviewing documentation, looking to see if there's a demo app for the SDK, because you can turn that demo app into a proof of concept, especially if the SDK doesn't verify request origin. You can quickly swap out the API keys and disclose information that way. Next is third-party plugins. This is more prevalent to React Native and Flutter, but you definitely want to audit plugins via static analysis, see if the plugins introduce any vulnerabilities, and looking into seeing what permissions the plugins that are in use have. Lastly, APIs. Reviewing the API documentation for curl requests will definitely pay off in the long run. Um, Documentation usually does have example curl commands because it's a real quick way to verify different functionalities of the API. And another thing you want to check to see is the web and mobile API different? You want to check mobile API request headers. For example, is there no CSRF token? Is there no XSS protection headers? Are there hard-coded authentication tokens that give you too much access? Um, is there the same authentication token for every user? This will lead to IDORs and all kinds of other different vulnerabilities potentially. This concludes my talk. I want to say thank you to Denise for inviting me to speak at Ekoparty, and I want to say thank you to the rest of the mobile hacking space team. I will be available for questions, and feel free to use any of these resources provided. Injured Android is available on GitHub and Google Play, and I used some of the CTF exercises from that application in this talk. I hope everyone has an amazing, epic, awesome day. Until next time, everyone.